Well, molarity is relating moles of solute to liters of solution. And so this can be very useful when we're doing stoichiometry if we have solutions instead of dry solids that we can weigh the masses of. So this is just a variation of grams to moles to moles to grams. So standard stoichiometry would be grams to moles to grams. But here, if we have a solution with a known concentration, we just learned how we can use the molarity to change volume into moles. So we could start with the volume of a solution and turn that into moles. And then at the end, if we end up with a different solution, we've got moles to moles, and then we can use the volume of the new solution to find the concentration. We can use the molarity of the new solution to find the volume. So, and then sometimes you might have grams to moles to volume, or volume to moles to grams. There's all kinds of variations. And that's why it's important to understand the big idea of how to approach these problems rather than trying to memorize a set way of doing problems. Because there's too many kinds of problems. It's just, nobody's brain has that much space. Let's do an example. What volume in milliliters of a 0.150 molar nitric acid solution will completely react with 35.7 milliliters of a 0.108 molar sodium carbonate solution according to the following balanced chemical equation? Is this a dilution problem? Doesn't say anything about diluting, does it? When you're diluting, you have the same chemical at the beginning and the end. Here we have a chemical reaction. We're starting with one thing, we're ending up with a different substance. So this is not dilution. This is stoichiometry. Think grams to moles to grams. Okay, let's highlight what they told us. We've got a molarity here. We've got a volume and another molarity. And our question, what volume in milliliters? There's our balanced chemical equation. I'm going to take these numbers just like I did with masses and write them underneath the equation so I can see what I've got. So this is the concentration of nitric acid. So here's nitric acid in the equation. So I'm going to write its molarity in there. 0.150 moles per liter. A capital M is way easier to type in the computer, but you're writing with your hand, write moles over liters. Over here, I've got 35.7 milliliters of sodium carbonate. So I'll put that in here, 35.7 milliliters of that. And then they're giving me the concentration of that one as well. 0.108 moles per liter. So what am I trying to find? Volume of HNO3. So that's my question mark. How much of this in milliliters? So we've got stoichiometry. We should first think of grams to moles to grams. And then look at what the question is actually giving us and asking us. It's giving us a volume in milliliters. So instead of that, I've got milliliters. And at the end, I want milliliters instead of grams. The molarities are moles per liter. The volumes here are in milliliters. And they almost always will be in milliliters because milliliter is a convenient unit to measure an amount of stuff that you might actually do a reaction with, unless you're doing an industrial process. But molarity is always moles per liter. So we have this issue with the milliliters and the liters, and there's a couple of different ways to take care of that. And I never have decided which one is best for Chem 1A students. So we'll go with this one. It's kind of in the middle. So milliliters to moles to moles to milliliters. Let's just see how that's going to work out. 35.7 milliliters. And I've got some fractions here. I'm going to have 3, as is pretty typical. That's milliliters of Na2CO3. And I'm going to go to moles of Na2CO3. Then I'm going to go to moles of the other thing. I really did not leave myself enough space here. And then milliliters. This is moles per liter. So it would be so much easier if this was in liters, wouldn't it? Remember that milli, that wasn't an M. Milli means times 10 to the what? -3. That's what milli means. So what I could do here is instead of writing the M, I could write what it means, and I will have transformed it into liters. So I'm going to take out the M and just write what it means, times 10 to the -3. That's a real fast way of converting from milliliters to liters. So then if I have liters down here, the liters are going to cancel out, and I'm going to have this moles per liter. In the middle, I'm going to have my mole ratio from the equation. So moles of Na2CO3. And now I've got those pesky milliliters again. So what we really need to do is add another step. We're going to go from moles to liters to milliliters. So I'm going to make that liters, and then I'm going to convert to milliliters of HNO3. This is a lot like what happened when we had a mass-to-mass problem where it was kilograms at both ends. So moles of nitric acid down here. Those units cancel out. Here I've got moles and liters of nitric acid, and that's what I was given, moles and liters of nitric acid.
Question.
Yes?
So we were able to just change it to 10 to the -3 in the beginning.
Mm-hmm.
Why did we not do that and just make the milliliters of
Why not just put times 10 to the -3 here?
Does that mess it up?
I would have to think about that. Yeah. I've never done it that way. Yeah, I don't think we can do that. Yeah. and then over here, HNO3. This conversion, we have milli in the top, and so we're going to write what it means in the bottom. If we put the milli up here, if we put the 10 to the minus 3 up here, these 10 to the minus 3s are not going to end up canceling out, and that's what they have to do. It's a good idea, though. So what ends up happening is this 10 to the minus 3 and that 10 to the minus 3 cancel each other out. So we have a mole ratio in the middle, and that just comes from the coefficients in our balanced chemical equation. 1 sodium carbonate for every 2 nitric acid. And this is where things get easier. Instead of needing to go calculate a molar mass, we're going to use the molarity that we were given. So for the sodium carbonate, it's 0.108 moles per liter. So 0.108 moles per liter. And over here, the nitric acid is 0.150 moles per liter. Moles is on the bottom, and so the number goes on the bottom. So I have 35.7 EE negative 3 times 0.108 times 2 divided by 0.15 and then divided by 1 EE minus 3. And this is giving me 51.408 milliliters. Any questions? If you didn't like doing this thing, it kind of feels like cheating, you can definitely add another step at the beginning and go milliliters to liters to moles. It's not the fastest, but if that's what makes sense to you and that's what you can remember how to do, then that's how you should do it, right? Because we're not going for fast and elegant, we're going for I can remember how to do it correctly. And even if that's a little bit slower, we want to do that. And that's why I'm not showing you some of the fancier things, because I don't want to confuse you. So this one's conceptual. We shouldn't have to do a lot of math. Consider this reaction, 2A plus B forming C. What is the limiting reactant if you mix equal volumes of a 1 molar solution of A and a 1 molar solution of B? If you have equal volumes and their concentrations are the same, what could we say about the number of moles? So solution A is 1 molar, solution B is 1 molar. Sometimes it's easier to think of things in concrete with, real numbers. So let's say we had equal volumes, 1 liter of each. If I have 1 liter of this, how much A do I have? So 1 liter times 1 mole of A per liter gives me how many moles of A? 1 mole of A, right? If I had 1 liter of 1 molar B, how many moles of B would I have? 1. This is not anything to do with the reaction up here right now. We're just looking at the solutions. If we wanted to write that out, we could say, 1 liter of this times 1 mole of B per liter of B, and that's going to give me 1 mole of B. It doesn't matter what these volumes are, it says they're equal. If the volumes are equal, the concentrations are the same, then the moles of A and B are going to be equal. In the chemical reaction, which one of them do we need more of? We need more A, right? We need 2 moles of A, 2 moles of A for every 1 mole of B. If we've got the same number, what's going to run out first? The A. So the A is going to run out first. That's going to be our limiting reactant. Does that make sense?